fundamental types of crystalline solids. So crystalline solids, we got regular repeating patterns to the particles. This is in contrast to an amorphous solid where there's no long-range order. But we can divide crystalline solids into 3 broad categories. And the categories are based on the individual types of particles. So we can have molecular solids, where the individual particles are molecules. So in that crystalline lattice, those structures we were looking at, each of those spheres would represent a molecule. We can have ionic solids, where those would be ions. And we can have atomic solids, where the individual pieces are atoms. And then this flow chart is showing how those are further broken down. Well, I guess I can't skip this part right here. So atomic solids then are broken down here by what holds the atoms together. Non-bonding, those would just be held by dispersion forces. Metallic, where it's held together by metallic bonds, or a network covalent, where it's actually covalent bonds holding the things together. So in a molecular solid, the composite units are molecules. An example of this would be ice, solid water. What holds molecules together to each other?
Bonds.
Well, there are bonds within the molecules, but between 2 molecules. Intermolecular forces. So you can have dispersion forces, dipole-dipole forces, hydrogen bonding. They vary in strength. But they are all much weaker than ionic or covalent bonds. So molecular solids tend to have low to moderately low melting points. Here's a couple of examples. Melting point 5.5 degrees Celsius and minus 95. So these things tend to be liquids or gases at room temperature. Some molecular solids can crystallize into different structures. So you can have the same compound and have it be in different crystalline forms. Those are called polymorphs. And those polymorphs can have different melting points, different solubilities, different densities, etc. Because how the molecules are arranged affects how many closest neighbors they have, which affects how strongly they're held together. So an interesting example of this is with chocolate. So cocoa butter is the main ingredient in chocolate. And how the cocoa butter solidifies affects the appearance and the texture of chocolate and its melting point. And so there's good chocolate and there's bad chocolate, and it's not all just what the ingredients are, it's also how it was made. And so there are different polymorphs of the cocoa butter, and here are the descriptions. So you can get a soft and crumbly chocolate. This is called blooming, and you'll sometimes see that on an old chocolate bar. You unwrap it and you're like, it's not chocolate looking, it's got all this kind of whitish stuff on it. That's not mold or anything, that's called bloom. It doesn't really affect the taste, but it does affect the texture, and it doesn't look very nice. Then you can get up to a firm one with some blooming. All of these will melt in your hand, and that's not the greatest because then you get all messy. This is the ideal one. You get a firm, good snap. You got a smooth and shiny surface. It will melt in your mouth, but not in your hand, which makes you think of M&Ms. But those are cheating. They've got a candy coating on the outside. And then there's another one that can actually take several months to form, and you can't form it from melted chocolate. So there's a science to making chocolate. And it has to do with how the cocoa butter molecules arrange themselves as they form a solid. So those are molecular solids. Ionic solids, we've got the composite units being ions. Ions are held together by ionic bonds. And so these crystals, instead of being separate molecules held together by weak intermolecular forces, These are repeating patterns of ions held together by ionic bonds. So these are going to be very strong. They're going to have high melting points. We'll talk more about these later. Atomic solids, you've got atoms. These would include things like solid xenon, iron, and silicon dioxide. You know, that looks like a molecule, but it isn't. So atomic solids can be divided further. We've got non-bonding atomic solids. Those are held together by dispersion forces. Because if you've got individual atoms, the only thing that can hold them together is dispersion forces. Dispersion forces are very weak, so atomic solids have very low melting points. Actually, the only examples of non-bonding atomic solids are noble gases in their solid forms. And those only exist at really, really low temperatures. Metallic solids are held together by metallic bonds. And we talked about this, the electron C model, where you have the metal atom and it sends out one or more of its electrons to be shared in this sea of electrons, and that's what holds them together. Metals have varying melting points. Some of them, like mercury, are liquids at room temperatures. Most of them melt at higher temperatures, but it can vary. And then network covalent atomic solids. The individual particles are atoms, but they're held together by covalent bonds. So these are going to have higher melting points than a molecular solid. Examples are diamond, graphite, and silicon dioxide. Graphene is another example of it. So here the crystalline structure is limited by the geometry of the covalent bonds. So we learned about that, right? We learned about Vesper theory and the valence bond theory with the orbitals and stuff hybridizing. And there's a limited number of geometries possible. Those are the only ones that can happen, and so you can't get closest packed structures. You're limited in the angles. These are going to have really high melting points because the covalent bonds are really strong. Okay, so you should be able to look at the formula for a substance and tell me what kind of a solid it would be. So, Au as a solid. What kind of, now they're telling you it's atomic, what kind of an atomic solid would that be? Would it be non-bonding, metallic, or network covalent? Metallic. So it's a metal, right? Au is gold, so this is a metallic. So if it's a metal, say it's a metallic atomic solid. The only non-bonding ones would be noble gases, and anything else we asked you about as an atomic solid would be a network covalent. And then we should be able to answer questions like this. Which solid would you expect to have the highest melting point? Magnesium oxide, iodine, or krypton? So what's holding these together? Well, this is an atomic solid, right? It's just an atom. And it's krypton. It's not a metal. It's non-bonding. It's a noble gas, right? So that's going to have a very low melting point, right? Here's iodine and magnesium oxide. So magnesium oxide is an ionic compound, right? And iodine is a molecule. Molecules are held together by intermolecular forces. Ionic compounds are held together by ionic bonds. What's stronger, an ionic bond or a intermolecular force? Ionic bond. So this should have the highest melting point because it has the strongest forces holding it together.